আমি স্টার্ট করি না? ওকে। No, this is a hello. This is a great pleasure for us. So due to some technical problem, we are late. So today we have Konstantin Novoselov, Nobel laureate who obtained his Nobel Prize in 2010. He will deliver his very important talks today, the materials for the future. So I would like to introduce the chair of this very important session, eminent professor of our time, Dr. Muhammad Alamgir, Honorable Member of University Grants Commission, Bangladesh, and who is the former Vice Chancellor of Khulna University of Technology, will chair this session. And along with Professor Alamgir, eminent education and business entrepreneur, Mr. M.D. Sabur Khan, will also another chair of these sessions. Now I request Professor Muhammad Alamgir to introduce Konstantin Novoselov and to start his very important talk. Professor Konstantin Novoselov, we are extremely sorry. There is some technical problem, so that's why we are a bit late. Please.
Absolutely no problem at all.
Okay.
Is it working? Thank you, Professor Shahadat. On behalf of the organizing committee, IC4IR 2021, I would like to welcome all of you who are in person in this Hall of Fame and who are connected with us virtually. This is the first plenary session. We are very proud to announce that our speaker is Professor Sir Konstantin Novoselov, and we are very much proud that he is with us, and we are also have our moderator Professor Shahadat, and we have also our guest is Professor Mr. Sabur Khan. And I would like to give some brief accounts about our keynote speaker, our first plenary session, that means our Nobel laureate. And he was born in August 23, 1974 in Nizhny Tagil of Soviet Union. After that, he studied in Moscow, and later he studied in Netherlands. He got his PhD in Netherlands. After that, he moved to UK and he studied and he do his research in Manchester. And in 2004, and he started his study, and in 2004 the material was rediscovered, isolated, and also investigated in Manchester University by Andrew Jim and him. And in 2010, they won Nobel Prize for groundbreaking experiment, 2D material graphene. It was huge discovery and has great impact on the research and development, especially on semiconductor, electronics, electric batteries, and composite. And you know that it has the valuable and useful nanomaterials due to its exceptionally high tensile strength and electrical conductivity, transparency, and the thinnest 2D material of the world. And you know that Sir Contestin was the youngest Nobel laureate in physics since 1971, and also he was the youngest Nobel laureate overall in since 1992. And in this conference, we are very happy to announce that he is accepted our invitation, and presently he is working in National University of Singapore. He is the first person who has been working in that university as a Nobel laureate. Now I would like to request Professor, our guest, and I would like to request Professor Constantine for his valuable deliberation. Please.
Good afternoon. It's really a great pleasure to be here. I'm terribly sorry I couldn't be there in person, but hopefully next time. So I've been collaborating with Bangladesh's PhD students, researchers over many years now. So it would be quite an important milestone in my research career to visit you guys. So can you see my slides? Hopefully, yes. So for today's talk, I would like to talk about the materials on the future, but probably the simplest way, the easiest way to start with is to start with graphene. Of course, one reason is that I've been working on this material for quite a while now, but also it does have quite a number of very unique and important properties, and probably even more important that it has a combination of a number of different exciting properties. So it's of course is the strongest material, is the most conductive, the most thermally conductive, impermeable, flexible, and so on, transparent, and so on and so on and so on. And because of all those properties, it has a chance, and it already has been applied for a number of different applications. So just ranging from composites to flexible electronics, from sensors to batteries, from optoelectronics to printable electronics. But even though it's very, very special for any physicist, it's quite interesting that it's also special. Well, it's not so special actually in terms of the applications, because it really followed the footsteps of many other advanced materials before it. For example, carbon fibers or carbon nanotubes. And some time ago, so people introduced it first in the composite materials for sports goods like tennis rackets, skis, and so on. Ourselves, we worked with Richard Miller and McLaren to create this world lightest, unfortunately also world most expensive watches. But then it just followed on, and soon it started to be used in car manufacturing, first in small niche applications, small car productions. But these days, actually, I should say that every single Ford car would have graphene under its bonnet, and the applications are actually quite interesting because it's not there for the sake of reducing the weight or increasing the strength. It's actually there for the sake of noise cancellation. You would probably guess it from the hindsight, because if you introduce 2D materials with a lot of interfaces, you would probably scatter phonons quite efficiently, but you really needed some work, for quite dedicated work of Ford engineers to come with this idea. And then further, more advanced applications, probably like I really like this Canadian company which utilizes graphene for speaker membranes, because for what is important for those speaker membranes is that it has it's light, and it's also stiff, and it's all graphene. And then going to more advanced electronic applications, thermal management. So lots of modern Huawei devices do use graphene for thermal management applications, because you can get thermal conductivity of 1000 meter Kelvin, and no any other materials can do it. So but these days a lot of truly electronic applications start to appear. For example, it is used for photo detectors, especially. It works well in combination with quantum dots, where you can tune selectively the absorption energy, and you can tune it to work in particularly any range, any wavelengths. So it's extremely important technology for autonomous vehicles, where you can introduce multiple sensors working in many different wavelengths. And of course, so what I would expect was going to happen, that it will be quite widely used for silicon photonics applications, and it already started to be used there, because the more signal processing you can do in the optical domain, the more efficient it will work. And graphene really allows, because of its high mobility, very fast switching in such silicon photonic circuits. If we need to look into the future, then I think the use of graphene as membranes is probably going to be extremely important, because of course it's impermeable to any gases, to any molecular or atomic species. But in fact we can controllably tune the permeability of those species through graphene by modifying graphene, and then we can use it for a variety of different applications, starting from biological membranes for tissue engineering or artificial organs, to various membranes, for example, for water desalination or ion separation. But what was, of course, a long time ago, we started our work with mechanical cleavage of graphite to obtain graphene. It's quite an efficient method, and we still use it in the lab quite widely. However, of course, it's not scalable, and that's why these days there are many other ways how to produce graphene in large quantities, depending on the quality you want to achieve and the price you want to pay. And so, for example, there is liquid phase exfoliation, which basically is similar method as mechanical cleavage, just done by via chemical routes, and it's quite fast and efficient, usually used for such applications as coating, composites, energy, bioprintable electronics, and so on. Or there is CVD methods, which you would use to produce large areas, square meterage, even square kilometers if you want, of high quality graphene for different electronic applications. And then there are also a number of niche epitaxial techniques, which also actually are being used these days for a variety of different products and different applications. But probably what's most important about graphene, that it actually gave rise to many other two-dimensional crystals to be discovered and studied. If you think that you get graphene by exfoliating lead pencils, you can probably exfoliate other pencils as well and try to produce other two-dimensional crystals. And the answer is yes, you can. And these days we're not only talking about uh, graphene. We're actually talking about the family of two-dimensional materials. All of them are only one atom thick or one unit cell thick, but they would cover, they would have all the different properties covering the range from most insulating like boron nitride to semiconducting like molybdenum disulfide to semi-metallic like graphene or metallic. So there are superconductors, there are ferromagnets. So really, so these days we have a huge choice of those 2D crystals. And it's really exciting to study all of them because physics in two dimensions usually very different than physics in 3 dimensions, and that's it's extremely exciting to study. But actually, there is even more important feature about our ability of obtaining two-dimensional crystals of different types. And let me just diverge a little bit from my talk and just give you a little bit of the background. So generally, materials are extremely important for human history. We even name our the ages we live in by the names of materials, like the Stone Age and the Bronze Age or the Iron Age. So the good question would be, which age do we live in right now? And probably for the first time in history, we have quite a choice for the name of the age we live in. We can call it the digital age, maybe, or the silicon age, or the nuclear age. One thing is probably that we need to be careful naming it, but also so it's important to make a smart choice. But maybe another question is that we probably shouldn't make a choice at all. Let me just give you an example of what I mean. So here is the periodic table of elements which have been used in silicon technology prior to 1990. You see, very, very simple technology. Silicon, boron, phosphorus for doping, aluminium for interconnects, then hydrogen, oxygen for passivation. Very simple. Even I could probably do it. Then after 1990, as the density of transistors increased, we needed more efficient, more conductive interconnects. So we started to use copper. Then that caused that we had to use also some materials to match the work function. We needed diffusion barriers, and that's why we expanded the range of elements we use in our technology. But it's still, the silicon technology still was reasonably manageable. These days, however, we use more than half of the periodic table, in our silicon technology. So the technology became extremely complex, and the reason for that is that we used something which we started back in 50s, 60s, and we keep adapting it for modern needs. And of course, at a certain moment, this adaptation became much more complex than the original technology. And the situation is actually quite bizarre, because if you compare the number of elements which we have in our body, in the human body, and the number of elements which we have in the integrated circuits, you would see that we actually have more elements. We use more elements in our silicon technology than there in our human body. So what it tells us, that probably at certain moment we shouldn't really bet on the old technology, on the single material we know well, and probably we should change and adopt new materials and switch the technology. Or maybe we should actually think about a new material for every new device, for every new integrated circuit. And that's where the 2D materials might be important, because it's of course very nice to study the properties of those individual crystals, and it's really exciting research, and lots of people across the globe do this. But it also gives us quite a unique opportunity, because imagine I have in my lab, when I enter my lab, I have those crystals all available to me as monoliths. So what I can do, I can start combining them and packing them back into the three-dimensional stack and start creating new materials, new crystals, new three-dimensional crystals, which do not exist naturally. And but we can design them in the lab, and we can design them to have specific properties or even specific functionalities. So we can make very interesting devices based on such materials, and we have made them already, like tunneling transistors, like photodetectors, solar cells. So this is an example of one of the most advanced materials. So this is an LED or a laser. So graphene plays only the secondary role here. So just thin layers. So it's a transparent conductive coating at the top and at the bottom, but the rest of the structure is by insulators and semiconductors. So we introduce those quantum wells inside, where we can inject electron and holes, and upon recombination they would give us some luminescence. So we can make light emitting diodes through this technology. So that's all great, and basically tells us that in principle the material science these days is on the level that we don't need to stick to one material. We actually can design on-demand materials for any specific application. So we're not limited to a few materials as we have been limited some time ago. We can actually create tailored designer materials for any new device, for any new applications. So that's the state of the art at the moment. But let me just go a little bit and look a little bit in the future and give you a hint. What are we actually doing now? What do we study? What do we research in the lab right now? And let me start with just giving you showing you this this image. This is of course just a small part of the Terminator movie. And for those who do remember, it's so the movie is set in 1991, and this robot travels back into 1991 so the movie was shot in 1991, and this robot travels back into the present from the future, and the future was set in 2029. So that's how back in 1991 we imagined our robots will be in 2029. They would be agile, they would be flexible, made of liquid metal, self-healing, changing forms, and so on. So we are in 2021, and so that's the state of the art for our robots. So I guess you would agree with me that we're quite a little bit away from our dreams. So the good thing is that we still got good 8-9 years, but still with the way our technology develops, I doubt we will be where we wanted to be. I doubt we will be able to make those liquid metal robots. And the reason for that is that our technology is fundamentally different from what is required for that sort of robotic capabilities. So our individual components in our technologies are not non-functional. The functionality only comes when you combine those individual components into a system. So the functionality only comes on the system level. And this is true not only about the clockwork making, and not only about robotics, but it's true about our electronics, bio and healthcare about our energy. And that's the issue. If you think about biological systems, they operate on completely different principles. They're much more, they have functionality which is spread across all the different levels. So individual proteins are functional, membranes are functional, individual cells are functional, organs, the whole body. So the functionality is spread across. And that's why we're so versatile and we're so flexible. And that's what we are proposing to do now, is to bring some functionality on the material level, create functional and probably even intelligent materials. By functional, I mean that they should be programmable to perform some complex response to external stimuli, and by intelligent, I mean that they would have memory, so they can learn and perform some basic functions. Just to give you an example, what do I mean? So I told you that we work a lot on membranes made from two-dimensional materials, and those membranes work well. But we can filter water, for example, with those membranes. So it is operational. But what we do now, we combine those 2D materials with polyelectrolytes, which are actually sensitive to chemical environment. And now, if those polyelectrolytes senses the presence of some poison, of some of different pH, they change their conformation and they can close these membranes off. And so here we don't need any sensor, we don't need an actuator, we don't need a computer to analyze the data. The material itself, the composite material, acts as a sensor and an actuator and as a computer. Here is another example which is developed by my colleague Guy Bazan here in the US. And so he grows bacteria together with conductive polymers, and those bacteria, they emit electrons as part of their metabolism, and then we can collect those electrons with the conductive polymer network or with the graphene network, and then we can create quite efficient batteries. But those batteries are actually alive because the conductive polymer and bacteria, they grow together synergetically. So, and we hope that we can use the same ideas to create new devices for electronics, where, for example, membristors can be used for neuromorphic applications, membranes and coatings. I gave you an example of the smart membrane, bio and healthcare, abiotic interfaces, energy applications, and so on and so on and so on. The issue, however, is of course the moment we start talking about memory for the material, we have to admit that our materials have to be operate out of equilibrium. And that's something which we are not very good at. Our current approaches in physics and chemistry only do the equilibrium calculations, and to do something out of equilibrium, we have to go beyond that simple approach. We have to do perturbation theory and so on and so on and so on. So we really have to design a new framework which can allow us to describe the dynamic dissipative properties of materials and predict the materials with the predetermined functions. Means that they predict the evolution of those materials. The way I like to describe the most challenging way is to how close can we get to the biological functionalities if we start with the non-biological component. And we do understand how those materials should be constructed, so we can think about, so we do know that the individual components need to interact strongly, and we do know that those components need to interact via multiple interactions like Coulomb, van der Waals, strain, elastic, and so on. And if you do this, if you follow these two basic principles, you can create materials where you have like a glassy state, a degenerate state with multiple energy minima, and then it will be very similar to the energy state of your proteins, because proteins they allow many different conformations, and then there is of course only one, which is the ground state, but in fact you have many closely spaced metastable states as well, and it's the possibility to go from one conformation to another, which allows you uh, to perform different functions and be so versatile. So as the individual components, we use many different materials which can interact strongly, and to interact strongly, we basically try to get rid of the bulk and focus only on the surface. But we also use the 3D materials, actually, especially those without bulk, like COFs and MOFs, and then we assemble them into the functional composites. And then if you assemble them correctly, you can tune them in such a way that they would react on specific stimuli with a specific response, but also would change their own conformation, their own structure, so they would have some memory effect as well. And we are trying to utilize those materials for a number of different applications, from electronics to energy to bio and healthcare. So quite a variety. So we have a lot of efforts on designing of the individual building blocks, but mostly the most challenge is coming when we start working through the properties, when we try to predict the dynamic properties of those materials. Because, as I said already, physical formalism is not so good, it's not very much suitable for that. So we have to use a lot of dynamic machine learning as well. And to get enough data for machine learning, we also utilize the robotic facility, which generate all those data. And then once we have this, we tackle a number of important problems in electronics, like neuromorphic computers, neuromorphic image recognition, in energy, like SMAP catalysis, in smart membranes, also biological membranes, bio and healthcare. So a good example is the smart drug delivery. For example, we can design a material in such a way that it would open and close the capsule depending on the immediate environment. Like, you probably get your vaccine through a shot these days, and the reason you cannot take a pill, you have to do it through a shot, is because the vesicles which deliver this vaccine are quite sensitive to your acidic environment in your stomach. So you have to deliver this vaccine directly into the bloodstream. If we can design our vesicles to be less sensitive, and to program it to go through your stomach and only open up in the inside of the cell, you will be able to you can really create very innovative vaccines. So one of the directions which is very active right now is the combination of 2D materials with polymers and polyelectrolytes. So we can design such composite materials to be reactive to a number of specific stimuli with some specific responses, but also change their own internal properties, internal structure. And then this way we really already achieved a number of exciting applications in ion separation, artificial tissue, drug delivery, and so on and so on and so on. And with this, I will probably finish here, and I will say that I think the future of materials is, first of all, in designer materials, which will be suitable for a particular application, but also in creation of the functional, intelligent materials, and with those we can tackle the world most exciting, but also most challenging tasks as well. Thank you so much for your attention, and it's really a great pleasure to join you here today. Thank you.
আমি তো কথা যখন আসছে
So, Professor Konstantin, do you have any time to take some questions from the audience?
Yes, just briefly.
Okay, thank you very much. May I request the audience, if you have any questions, you have the chance, please. And please give the microphone to the audience.
Professor Konstantin, it was a great talk on materials, but you pointed one thing, something very, very exciting and interesting, is that adaptive intelligence. Can you tell us in the future material of graphene, is there any way we can incorporate intelligence at the level of molecular binding? Some kind of intelligence that can help to evolve the material by itself? Thank you.
Right. I mean, that's of course the most important question, and that's the key question, and that's the question for me. Where is the border of intelligent and non-intelligent structures? And it is closely related to the question of complexity. So intelligence probably is related to complexity. So for me, ourselves, we separate the functional and intelligent. So functional are the materials which we can program. So they change when a certain stimuli comes, and then they change back when the stimuli goes away. This is quite exciting already, but it's simple. Intelligence for me starts when you get memory, when you can learn, and when you can memorize something, and that's a little bit more. That's more difficult. It is possible. I think it is possible to do on molecular level as well. So we can create materials which say can learn, and then if we absorb 10 molecules of one type on the surface, it will be easy to reduce the barrier to absorb the 11s, and it would block the others one, and so on. So I think we can design this intelligence in the basic form. So for me, memory hysteresis is already the onset of intelligence. How far will we go? I don't know.
Okay, thank you very much. Now, any more questions, please?
Yes. Konstantin, Professor Sajjad, Добрый день.
Добрый день.
Do you speak Russian?
I do speak Russian, yes.
Yes, thank you very much.
Yes.
Очень приятно вам visit University Grants Commission. We're very pleased and very happy you were here. So I have a question. The question is, you showed about living organism and living, their cell is, the cell is in, not this one, before you, some slides that I'm a computer quantum guy. So computation level, do you have any possibility that we can compute in living cells. Do you got my question?
Yes, I do. First question is, what is living? So it's the same question as before. Where is the border of intelligence, and where is the border of living, right? And say, are individual proteins alive or not? Probably not. But are viruses alive or not, or bacteria alive or not? So where is this border? So I'm really far from claiming that I know where to put this border. So for me, I would say that in terms of materials, it will be probably very challenging to create materials which reproduce itself. So I decided that we don't put this into consideration. But then what is the next one? And the next definition of being alive. So for me, that's again this ability to make decisions, and ability to make decisions means that you have your background, you have your experience, and that's again learning and memory. So again, we're extremely bad in describing systems with hysteresis. So that's something which we are trying to develop a framework how to describe those. So we have some progress in terms of the dynamic machine learning, which we have some indications that probably hysteresis is the representation of some hidden variables, which actually, if you introduce those hidden variables, your system becomes non-hysteretic, but in those hidden variables. So it really brings very, very fundamental questions in mathematics and in life science probably. So I won't be able to answer you directly, but I think we can describe. So if our approach is correct, that smartness and memory and hysteresis can be described through discovery of the hidden variables, then we really have something in hand, and it will really be a huge breakthrough.
Okay, thank you very much. Do you have any more questions? Maybe we can take 2 more questions, please.
Hello, Professor. Can you hear me?
Yes.
Yes, thank you. It's an outstanding talk, actually. You have shown so many applications which actually related many real-life problems solving. So one of the important contributions you highlighted about robotics, I'm sure that you are mentioning about soft robotics. Am I right?
We actually have, by robotics, I mean that we have, so we use robots to create materials to collect data, but we also can produce new types of robots with our materials, and that would be soft robotics. Yes, you're right.
Yeah. And our country is such a country where sustainable development goals is very important, and disability is an important issue here. So we are focusing on technology for the benefit of humanity. Would you please shed some light that how your materials can be used in robotics, and how those robotics can be used for disabled community? Any applications you can guide us so that we can guide our young generation? Thank you.
Right. Yeah. This is a very good question, of course. And I mean, I'm a scientist. I'm a physicist, material scientist. So I'm a little bit far away from the final end application. But one of the research, one of the direction we are trying to work on is exactly the tissue engineering and the artificial organ engineering. And I think with the moment you produce smart materials, it will be much easier to create artificial tissues and artificial organs, because it will be much easier to program those materials to do certain functions. So we do have some work on artificial kidney, on artificial skin, and I think it's a very, very promising direction for functional intelligent materials.
Okay, then thank you very much is there any questions from the audience? We can ask one more questions because we have the next session also. Okay, I think there is no more questions from the audience. Can I ask one questions to you? So how far we are to produce the similar nature of materials like human skin? Is it possible to produce that kind of materials in near future? How far we are from your perspective or from your experience?
Well, I would say, I mean, human skin is.
Yes.
I mean, any human organs are extremely complex and have multiple functions. And skin, probably one of the most complex, because you have sensors, you have evaporation pores, you have it's a barrier. I think we are actually quite good at making. Fulfilling at least several of those functions. To make a material so universal as skin itself, I think we're still far away. But creating small patches which are protective, allow some electrical signals to penetrate, allows water through when you need to evaporate it. I think we can do at least some functions quite well already.
Okay, thank you very much. And at the end, I would like to apologize from the organizing committee for making delay for you, because your presentation started almost 15 minutes delayed. We are very sorry because it is due to the internal arrangement, there was some unfortunate delay.
Now it's very clear that these days organizing a conference is a heroic action anyway.
Yes.
So I really congratulate you on this. Thank you.
Yeah, nevertheless, we enjoyed very much your outstanding presentation, and our audience enjoyed very much. And you are the first speaker from the Nobel laureate, and you are one of the youngest Nobel laureate, and you have a long experience, and your research has a tremendous impact in our daily life. Also, it has tremendous impacts on our future, because we are heading to fourth industrial revolution, and we are heading to fifth industrial revolution also. And in that case, robotics and other things play a very vital role, and people, human and robots will work together. In that case, material will play a very important role. So at the end, I would like to congratulate you for being with us on behalf of the organizing committee, and please give a big hand to our speaker.
Thank you so much, and I really hope that I will be able to visit Bangladesh in the near future. Thank you.
And we would like to see you in person in Bangladesh, and this time we missed you due to the COVID-19. We hope in future University Grants Commission of Bangladesh will invite you, and we have an open invitation for you. Anytime, if you have the time, please come in Bangladesh and see the amazing people and amazing development of Bangladesh. And we are expecting you in Bangladesh. We will welcome you anytime. Thank you very much, because Singapore is very close to us. Okay.
Yes.
So again, we have a big hand to Professor. So with this few word, I would like to conclude this session. Thank you very much for your nice presence in this Hall of Fame.